Hello and welcome back, everybody. This is going to be the example problems for net ionic equations. The notes definitely do not do it justice. This is definitely one of those things where you will want to be watching this video and it will help you kind of fully understand what's going to go on in these problems. So we've got three examples that we're going to work out. We've got one that is lead 2 chloride, specifically, lead chloride. I'm going to try to get better about moving my hand out of the way. That is one thing I'm noticing that I'm kind of making mistakes on when I do this. So, plus calcium nitrate. Our second example is going to be mercury 1 acetate and lithium fluoride. And then our final example is going to be calcium bromide and sodium acetate. All right. Hopefully I just adjust the lighting and this might work a little bit better and I won't cast as many shadows. So we'll start with our first example, lead 2 chloride. And calcium nitrate. So our first step is obviously going to be to translate this. Lead is Pb. It's Pb with a +2 charge because it's a 2. Chloride is Cl, that's a 1 minus charge. We cross our charges, we will get PbCl2. Calcium nitrate, Ca is for calcium, that's a 2 plus charge. Nitrate is NO3 with a 1 minus charge. So we'll get CaNO3 2. So there's our first two pieces. Now, most of the problems you're actually going to work out, and you'll see this on the worksheet that I'll post. You will have a ME, which stands for molecular equation. You will have a CIE. We'll actually do this down here. CIE, and then you'll have a NIE. So this is molecular equation, complete ionic equation, and net ionic equation. First thing you want to do, once you have these pieces, so these are going to go on our molecular equation. We've got PbCl2. I'm going to leave a gap here because remember we're going to have to go back and add a state of matter. And I'm also going to leave a gap, I'm going to leave a gap here because we're going to have to go back and add a state of matter. And I'm going to leave a gap here for whenever we're balancing if we need to do that. So then we'll do a plus, and then we'll take our CaNO3 leave a gap for balancing if we need it, and we'll put Ca parentheses NO3 2. And then we can put an arrow. Now we need to look at the elements that we've got and determine if they're soluble. Now you don't have to write this all off to the side, but I am going to write it off to the side just so I can point to it a little easier. So I've got PbCl2 and we've got CaNO3 2. Looking at CaNO3 on our solubility rules, does it contain a group 1 cation or ammonium? No, it contains a group 2, no ammonium. Rule 2, does it contain an acetate or a nitrate? Yes, and the name was right there. It's got a nitrate in it. So because this has a nitrate, this is going to be soluble. And because it's going to be soluble, we'll go back here and we'll add a little AQ that even though I mentioned it, I did not leave space for. And to make this bigger so you can see what I'm writing, this is a AQ for aqueous. Okay, what about for PbCl2? Does it contain a group 1 cation or ammonium? Nope. Does it contain an acetate or a nitrate? Nope, doesn't contain either of those. Does it contain a halogen? Yes, it contains a fluorine, chlorine, bromine, or an iodine. In this case, it contains a chlorine. However, does it also contain a silver, lead, or a mercury 1? And in this case, it contains a lead. So because it contains a lead, that means that it is going to be an exception to that rule. Because on your solubility rules, if you have them close by, it says they are soluble except the ones that contain these things. So since it contains lead, since it contains Pb right here, that means that it's going to be insoluble. And that means we're going to put a little s. Now these are going to be your favorite. Because PbCl2 will not dissolve in water, we can't do anything. There is no experiment, there's no science, there's no anything to be had in this problem. You're going to put this in and this will dissolve. You can stir it around, you can get it to dissolve, but this is just going to float in there. So there's not even a chance for a reaction to occur. There's literally nothing is going to happen with one of those pieces. If even one of these stays solid, you automatically get to say there's no reaction. And that means that you don't have to put anything on the next two lines. So those are going to be your favorite types of problems. Now for our next example, we've got mercury 1 acetate, and we've got our lithium fluoride. Same thing, first thing we have to do is actually translate them. Mercury 1 is like one of the biggest jerk moves that any of the scientists do because it is a polyatomic. It doesn't look like it would be. You would just think it's just Hg with a +1. But Mercury 1 is actually Hg2 with a 2+ charge. And acetate is C2H3O2 with a 1- charge. And then lithium is Li. Lithium has a 1+ charge, so just a plus, and then fluorine is F, and it has a 1- charge. So if we cross all of our pieces, again, I'm gonna scoot over here actually for convenience sake on being able to see this stuff. We'll get Hg2 C2H3O2 2, which normally you would think you could reduce this, but since this is a polyatomic, you can't reduce inside the polyatomics. Again, it's weird because it's just Hg2, but you cannot reduce it. And then over here we'll have LiF, lithium fluoride. Okay, first one, does it contain a group 1 cation or ammonium? No, it does not. Does it contain acetate or nitrate? It contains acetate, so this means this is soluble. That will dissolve. And then LiF, does it contain a group 1 cation or ammonium? Yep, it contains a group 1 cation. Lithium is in group 1, so that one's also soluble. That means we actually get to do the problem. So we'll start with our molecular equation. Our molecular equation is Hg2. I'm going to leave a small gap here in case I need to go back and balance it. So let me box this off. I would not recommend boxing it. It just makes it look super messy. So in fact, we're gonna there we go. Okay, so we've got Hg2 parentheses C2H3O2 2. Leave a gap so you can add state of matter. Plus, leave a gap so you can add something if you need to balance it. LiF, leave a gap so we can add state of matter. And then arrow. Now, we actually know the state of matter because we've been going through, so I'm going to go ahead and add them, my AQ and my AQ. And now we swap. We take the first pieces for each of them because it's a double replacement reaction, and we're going to swap them, and we're going to recross our charges. So now we're going to get Hg2 and F, which will give us Hg2F2. And we're also going to get, now the Li and the C2H3O2 will be together. So I'll do that over here. So we've got Li, C2H3O2, but this one is just a +1 and a -1. So that's just going to be Li, C2H3O2. And I didn't leave a space here because I'm bad, but we're going to need to go back and add states of matter for this side as well, but we can balance it while we're waiting. We've got 2 Hgs, 2 Hgs, 2 acetates, 1 acetate, so we'll put a 2 there. We've got 2 lithiums, we've got 1 lithium, so we'll put a 2 there. We've got 2 fluorines and 2 fluorines. Okay, now going back to our rules. For lithium, it is from group 1, so it's soluble. We can put an AQ there. We know that's going to be aqueous. But then for Hg2F2, doesn't contain group 1 cation or ammonium, doesn't contain acetate or nitrate, does contain a halogen, and contains fluorine, but this one is another one of those exceptions. It says silver, lead, or mercury 1, and this is mercury 1, which means this is going to be a solid. Hopefully you left a little bit more space than I did, so it's a little bit neater. So there's our molecular equation. We've got our full written out. If we kind of ignore this chunk over here, because that's a separate thing, this piece right here is our molecular equation. Now we're going to do the most annoying part of this whole process, which is we're going to convert this into a complete ionic equation. We're going to take account of every single ion that is in this reaction as it is currently situated. So these are aqueous. That means they split apart. So that means that when this splits apart, you're going to have an Hg2 with a 2+ charge that is aqueous floating around. Plus, these guys are no longer going to be tied together because they're no longer in a compound. So we're going to have 2 C2H3O2 minus that is aqueous, that's floating around. And if you're like, this seems like a lot of writing, you are correct. And you have to do this for every piece that is aqueous. You might have been wondering why you had to split the ions apart whenever you were doing the solubility rules worksheet. Now you know the answer why, because you're going to have to be doing a lot of splitting apart. So in this case, notice there's a 2 out front. We still are going to keep track of that 2. We're still going to keep track of all of our amounts of substances. So because we balance this with a 2, we will put a 2 in front of the Li and a 2 in front of the F. And they are both aqueous, plus 2F, that is a minus, that is aqueous. And then we're going to put an arrow. Now I'm going to list this one first just because it's kind of how I like to do it. Because this one is still aqueous, I will still have 2 Li's that are pluses that are aqueous, and I will still have 2 C2H3O2s that are A minuses that are aqueous. But this last piece is a solid. And if you remember back to the rules that PowerPoint slide was saying, let me actually pull it up on my computer so I can mention what it is real quick to make sure I'm quoting correctly from there. Keep any other states of matter other than aqueous together. You do not split them apart. So this thing actually, when they react, they'll turn into a solid and it will precipitate, which if you remember, precipitate means when you pour it in like precipitation, it will fall out. It will actually, when you mix them together, you will get a solid that will form from them. So these pieces, this solid actually stays together. You get Hg2F2, and that is a solid. Okay, complete ionic equation is finished. Now we just need to do our net ionic equation. Net ionic equations are way easier. Complete ionic equations were complete. They had every single thing in it. For net ionic equations, if you think like your net money is your money after everything has been taken account, like that you've had to pay to taxes and stuff is there. It's your total that you have at the end of the process. So we're going to get rid of every piece in this that is the same thing on both sides. So I'm going to switch to a different color. We have an Hg2 plus 2 aqueous. We don't have one of those over here. We have 2 C2H3O2s that are aqueous and minus 2 C2H3O2 minus that is aqueous over here. So we're going to go ahead and cross those out. Those are going to disappear. Now on your actual worksheets, you would want to do this to make sure that I could still see what you had written here, because I have to give you points for those things. But you could also put like a little cross mark underneath it or a check mark underneath it, or you could just do it in your head. You don't actually have to physically cross them out if you don't want to. But I'm going to cross them out just so it's easier to see. So we've got 2 Li plus aqueous, 2 Li plus aqueous over here. We'll cross those out. And then we've got 2 F minuses that are aqueous, and we don't have that over here. Again, there is Hg2 and there is 2 Fs, but they are not exactly the same. They are not exactly the same pieces on both sides, so they do not cancel out. And now that we've gotten rid of the stuff that didn't actually do anything cool, remember the whole point here is to figure out what actually is doing something in this reaction. So now we know what is the thing that's going to actually do something. It's actually going to do something cool other than exist next to each other. And that's going to be our Hg2 plus that is aqueous at the beginning, and then our 2 F minuses that are aqueous at the beginning are going to combine together and are going to form an Hg2 F2 solid. So this lithium acetate even though it is being formed by this experiment, it's actually just aqueous. So it's really going to just float around in the liquid. You would have to like boil off the liquid or do some sort of extraction or do some other sort of process to really get lithium acetate like crystals or solid out of it. You would have lithium acetate in the liquid, but that's because you would have lithiums and acetates floating around in the solution. It's the same thing that when you take a like sodium chloride and you put NaCl into our cup of water, like we talked about before, in that water there is going to be Na pluses and Cl minuses. There's not actually going to be any NaCl in the water. There's just going to be the two floating around. Same thing here. There won't actually be any lithium acetate. There will just be lithiums and acetates floating around in there. So this is our net ionic equation. That is our final answer. Now, I'm running a little bit tight on space for this next one, so we are going to flip the page. We're not going to play that game and just, accidentally end up with not enough room to complete this. So our last example is calcium bromide. And if you're wondering how I ran out of space so soon, I did other examples on the top of that page, trying to be eco-friendly here. We have calcium bromide. There it is. Calcium bromide. Calcium bromide plus sodium acetate. So calcium is Ca with a 2 plus, bromine is Br with a 1 minus. Sodium is Na with a 1 plus. Acetate is C2H3O2 with a 1 minus. So that means for the first part of our reaction, we're going to have CaBr2 and NaC2H3O2. All right. Does this contain a group 1 cation or ammonium? Nope. Does it contain an acetate or nitrate? Nope. Does it contain a halogen? Yes. Does it also contain silver, lead, or mercury? No. So it contains a halogen, but not one of the exceptions. That means this is soluble. Does this contain a group 1 cation or ammonium? Yep. Sodium is group 1, so this is going to be soluble. Okay. So that means we do get to actually go through and do our experiment. It will actually have some kind of reaction, quote unquote, at least at the beginning stages. So for our molecular equation, we've got, again, leave a gap. I'm actually going to, because I keep forgetting, we're gonna put a line there. So we've got CaBr2. We know it is soluble, so it is aqueous, plus line NaC2H3O2 that we know is aqueous. I'm going to put an arrow. So now we're going to swap our first pieces. That'll give us NaBr and CaC2H3O2. For NaBr, does it contain the group 1 cation or ammonium? Yes, so it's soluble, because sodium is group 1. For number 2, does it contain a group 1 cation or ammonium? Nope. Does it contain an acetate or nitrate? It contains an acetate, so that means it is soluble. So you'll notice this is the difference in this example. We have all soluble stuff here. Those of you that are paying more attention to this will probably have realized where the real difference is going to lie, but don't worry, we'll get there as we kind of move through it. So I'll go ahead and write our NaBr AQ. Make my B look a little bit more like a B. Plus, and then our Ca parentheses C2H3O2 2. That is also aqueous. Now, the only problem here is that because all of them are aqueous, for our complete ionic equation, we have to separate everything. So every single one of these pieces. First, we got to make sure it's balanced, though, so we know that we're actually keeping track of everything. This needs 2 acetates, and this needs 2 bromines, so we're going to end up having to put 2s there to get it balanced. So now we're going to take, and we've got a Ca, that's a 2 plus, that is aqueous, plus 2 bromines that are minus, that are aqueous, plus 2 sodiums that are pluses, that are aqueous, plus 2 acetates, C2H3O2s, that are minuses that are aqueous. And you have to include every single piece. You have to include the aqueous, the negative, the subscripts that are in the actual thing, and the coefficients out front, all of it. And then we'll do another arrow. We've got 2 NAs that are pluses that are aqueous. We've got 2 BRs that are minuses that are aqueous. We've got 1 CA that is a 2 plus that is aqueous. And we've got 2 C2H3O2s that are minuses that are aqueous. Oh my gosh, so much stuff. Okay. Now we have our complete ionic equation. Now we want our net ionic equation. And this is where the difference lies, because last time we had something that was solid. We had something that changed in this case. So even though this will quote-unquote react, as I hit my camera, how many times am I going to do that during this process? Oh, God. So as we react these together, as we put this in the liquid, you're not actually going to get any solid. Like the last one we did, if I pull up that sheet, we actually got something cool that happened. Like we mixed 2 liquids or 2 solids together. They dissolved, and if we would have poured these liquids into each other, we would have gotten a precipitate. We would have gotten something that changed color, kind of like that lead and potassium iodide that I poured together. And it's 2 clear liquids you pour in, and you get a yellow color out of it. But this one, everything just stays dissolved. There's nothing that's actually going to form together and precipitate out, which means as we go through this, we've got a Ca with a 2 plus, we've got a Ca with a 2 plus, we have 2 Br minus, we have 2 Br minuses, we have 2 Na pluses, we have 2 Na pluses, we have 2 acetates, we have 2 acetates. We are left with nothing as I hit the spring on my stand for my mic and camera. So because we are left with nothing, there's actually a second opportunity for no reaction. And in this case, we have it. There is no reaction when these two mix together. Now, this gives us the 3 categories. And this is kind of what I'm thinking I'm probably going to have you do for the worksheets there. Instead of having you type this, because, I mean, you could get the formatting of doing a superscript and a subscript and all of that stuff. Like, that is a thing that could happen. But man, I wouldn't want to have to type that, and I wouldn't want to make you have to type that. So we're going to probably put this into 3 categories, and I'll go ahead and give you these now, and then you kind of can know the way that I will describe them. So there can be no reaction at molecular equation. You can have no reaction at net ionic equation, or you can have a reaction. And if you have a reaction, I would want you to list and tell me what is it. Like, what do you actually get from that reaction? So I'll probably have questions like this instead, where it just says, like, what is the result of these two mixing together? You could say no reaction at molecular, no reaction at net ionic, or reaction because this will form. So I hope that kind of makes sense. Whenever I upload the actual assignment that'll go with this, I may actually I will also give you the assignment that has the lines written out just in case you have printing capabilities, so you can print it out and try to do them on paper. But the assignment thing that I'll actually have you do for points and turn in will be something more like this. I think it's just going to be easier for everyone involved. I hope that makes sense to you guys. If you have any questions, write them in the box to the right or send me an email. Hope everything is going great in your life. Hope to see/hear from you guys soon.